Welcome back, everyone. Today we're going to work through our cylindrical coordinates group work. Problem 1 has us setting up but not evaluating an integral. So here we're just translating. So here's our integral where E is the solid in the first octant that lies under this paraboloid. All right, so to set this up, we already have our function, but we'll need to figure out our limits of integration and using cylindrical coordinates here. And so to figure out our limits, right, we need to figure out the region that we are integrating over. And so let's get a picture going. All right, so our paraboloid is going to start up at 4 on the z-axis. And is going to open down, right, as an analogy, right? If this was y equals 4 minus x squared, then this would start at y equals 4 and move down on either side. Here we have kind of a higher dimensional version of that. So here our paraboloid is going to be kind of coming down all over. And we want the part of this that's in the first octant. And so here's our paraboloid. We want the part that's only in the first octant here right in front of us. And so this paraboloid is going to get cut along that xz plane, the xy plane, and the yz plane. And so we're just going to see kind of a quarter of it, right? And the backside would be hugging these axes here. All right, so we see this quarter of our paraboloid. All right, and so to start, we need to pick a variable to move first. And so I think let's think about moving z to start. That seems pretty natural. If we pick an xy and move in the z direction, well, we are starting at z equals 0, and then moving up, and then blink, coming out on our paraboloid. And if we pick something else underneath this, those are going to be consistent instructions, right? Start at z equals 0, move up, and then blink, come out at the paraboloid. So we get consistent start-stop instructions, so we can set up our innermost integral, moving z from the bottom, z equals 0, up to the top, which is our paraboloid, 4 minus x squared minus y squared, already solved for z for us. All right. Our next question is, for what xy's do we do this for? In other words, what's the shadow of our quarter paraboloid chunk here? And so that shadow is going to live in the xy plane. And we can imagine if we had a flashlight up top, right, just shining on our pink part here, we'd only see this quarter, right, in the first quadrant, because we looked in the first octant up here. So the shadow here, right, is going to be this region at the bottom. That's where our kind of quarter is largest, widest. So we get this as our shadow. And so from this, we can see that this outer edge is going to come from where our paraboloid intersects the xy plane, i.e. it's going to come from the trace at z equals 0. All right, so if we want to figure out the trace of our paraboloid there, substitute z equals 0. And if we add the x squared y squared over, we see that, this is a circle of radius 2. All right, and so this has a nice clean description in terms of polar. The angles we're using, right, are from 0 up to pi over 2. And for each one of those angles, like this one, we want to start all the way at the origin, so r equals 0, and then move out to r equals 2. All right, so these become our descriptions, and again, since we're describing the xy plane in polar coordinates, our x is r cosine theta, y is r sine theta, and we have our nice Pythagorean theorem identity, x squared plus y squared equals r squared. And so with this, we can start translating our integral, and we have our function, x plus y plus z, and we moved z first. And then we describe the xy plane in polar, so we'll have r dr d theta after that. And let me actually slide that r right here in front of the dz, dr d theta. And then for our other integrals, so we said we're moving r from 0 to 2 and theta from 0 to pi over 2. And we're almost there. We just have to finish translating our integral. The only variables we want to see are z, r, and theta. So we want to get rid of our x's and y's wherever those show up. And so here in our function, we can just swap in what x and y are through our translation equations. But up here, the minus x squared minus y squared, we can pull out that negative, and we can use our Pythagorean theorem identity to translate that nice and clean. So here we go. So theta from 0 to pi over 2, r from 0 to 2, z from 0 to 4 minus r squared. Then on our function, we have x is r cosine theta plus y, which is r sine theta, and then plus z times that r. And see if I can fit it in here. I'm running out of room. I'm just going to do it vertically, dz dr d theta. And there we go. Our integral is fully translated into cylindrical coordinates. Our second question I actually address in another video. The link will be supplied in D2L, but also you can get there quickly just with this bit.ly URL. You just enter bit.ly/cone and sphere. And I think you do have to be careful about the capitalization. That'll get you there real quick at the right time. All right, this next question has an integral that is probably most appropriate in rectangular, but here we're going to do things the hard way and translate this into cylindrical coordinates just to see how that goes and get more of a feel for how these coordinates can work. Okay, so if we want to translate this integral into cylindrical coordinates, let's first get a feel for the region that we're integrating over. And so here the instructions for z tell us to start at 0 and stop at z equals 8 minus 2x minus 4y. And so this is going to be a plane. Let's start getting a picture here. All right, so graphing our plane z equals 8 minus 2x minus 4y. At xy equals 0, this thing's going to have a z value of 8. And if we want to get our other two axes intercepts, we can quickly find those. If we set, we want to find the x-intercept, we can set z equal to 0 and y equal to 0. And so it looks like x is going to be 4. So 8 up here, 4 over here. And then our y-intercept, let's set x equal to 0 and z equal to 0. And it looks like y is going to be 2. Here we go. And so here we get a nice triangular chunk of the plane we're looking at. Right away, we don't necessarily, without any more information, know that this is the only part of the plane we're looking at, but if we consider our other limits of integration, we can figure out which part of this plane we are looking at. So the other limits are in terms of x and y. Our limit here tells us to start x at 0 and move it to 4 minus 2y. So x equals 0 starting, and then moving to x equals 4 minus 2y. This is a little bit awkward in that form. We like y equals. Let's switch this around. We get 2y equals 4 minus x, or in other words, y equals 2 minus 1/2 x. So we can graph that. Y-intercept is going to be 2. And slope minus 1/2. And we will intersect the x-axis at 4. And if we look at the answer to the question of what y's do we do this for, we're doing this from y from 0 to 2. And notice that is exactly giving us this line segment here. And so with this as our shadow and this is our plane, it looks like we're integrating over the region that our plane cuts out, this tetrahedral region with the first octant. So we have this plane on one side, and then it hugs the x, y, and z axes on the back. All right. So now that we have a feel for our region that we're integrating over, let's think about how we want to move through this. Well, there's no reason we can't keep moving z to start. And so here we're moving z from 0 up to the plane as before. And so we can actually just keep the same inside integral for cylindrical. So move z from 0 up to 8 minus 2x minus 4y. All right, but then the question is, well, what's the shadow that we get in the z direction? In that shadow, if we imagine a flashlight up here shining down, right, the shadow we'd get, the widest part that we're covering in the xy plane is right here, this triangular region that we've seen before. All right, and so, well, how can we describe this in polar? Right? It's not very natural, and that's the idea here. We're trying to do something to kind of flex our cylindrical and polar muscles. Well, what angles are we using? Well, we're using angles from 0 up to pi over 2. But notice, depending on what angle we choose, we always want to start r at 0 to get the origin. But where we stretch out to, that length, is going to change depending on our angle. Right? When our angle is 0, we're going to stretch all the way out to 4. When our angle is a little bit bigger, we're going to stretch a little bit less. Increase our angle, we're going to stretch a little bit less. And at pi over 2, we're going to only be stretching out to r equals 2. And so where we're stopping r, it depends on theta. what we need to get a hold of is this line that we're stopping at. And what I mean by getting a hold of is get an equation, right? And we actually have one. So we have our equation, and what we need to do is translate that equation into our polar coordinates, and then we'll be able to solve for r. That'll tell us the r that corresponds to each theta. So here we go. X in the xy plane, this is our r cosine theta, equals 4 minus 2 times r sine theta, and for y. The idea here is now that things are in terms of r's and theta, well, let's just solve for this r that we want to find. So if we add the 2 sine theta, we'll get r cosine theta plus 2r sine theta equals 4. And now we can take this r and pull it out. Cosine theta plus 2 sine theta equals 4. Then we can divide by that coefficient. So r is 4 divided by cosine theta plus 2 sine theta. This is the answer to the question. Well, given a theta, what r do we want to stop at? It's this one. This is what it ends up as. And so with that, we can put our full integral together. We've already found our inside-most integral. All right, we're moving z from 0 to 8 minus 2x minus 4y. And let's actually right away, let's swap out x and y for what they are in terms of polar. So minus 2r cosine theta minus 4r sine theta. And our function was arctangent of y, if I scroll up just for a second. And so we can also swap out our y there as well, translate our function. Arctangent of r sine theta. And once again, the dx dy, that becomes our r dr d theta. And I'll slide the r out here. Dr d theta. And right, for the thetas from 0 to pi over 2, we're stretching r from 0 up to our big ugly formula that we found. Cosine theta plus 2 sine theta, giving us the correct place to stop so that we land right on that line. And stop where we should. All right. So there's our integral. I'm just looking through to make sure it's all fully translated. Don't see any x's or y's still there. And so we're good. All right, our next problem is similar, but in this case, changing to cylindrical is actually going to be helpful. We're going to get a much cleaner integral from there. And so let's play our game here and figure out how to do this. Once again, we can, if we'd like to, just see what happens when we just keep z as our rectangular coordinate for cylindrical. Here we're moving z from 0 up to 9 minus x squared minus y squared. So here, this is giving us another paraboloid opening down, and on the z-axis it would intersect at 9. Let's get a picture going just to help ourselves think about this. And so we have our paraboloid opening down. here we're at not 8, but 9. All right, and so as we move z, we're always starting at z equals 0, so the xy plane, and moving up to our paraboloid here. And let's look at the description of our shadow. So from this, we can get a sense of the shadow in the xy plane. Looks like for x's from -3 to 3, we're moving y from 0 up to root 9 minus x squared. And this root 9 minus x squared, this should stand out to us as the top half of a circle of radius 3. Right, and we're always moving y, when we set an x, moving y from 0 up to this curve, and we're doing that for all these x's from -3 to 3. So it looks like we are tracing this out as our shadow. So coming back over to our three-dimensional picture, looks like we're only getting 1/2 of what we're seeing here in our picture. So this portion with y being 0 or positive, right, and this here in the xy plane as our shadow that we saw. All right, so in cylindrical coordinates, we can describe this region pretty nicely. So we're using angles from 0 up to pi. And for each one of those angles, like this one, we have the same instructions for r, right? Always starting r at 0, and then stopping r at that boundary when r is 3. So nice, clean description. And since we're using polar coordinates for our xy plane, we have our standard equations that we can write down, and we can start translating. So our integral, moving z from 0 up to, do the same trick as before, 9 minus r squared. And then in our function here, we're also going to get a similar thing going on. Root r squared, which technically, in general, gives us the absolute value once we take the square root of a square. But r, as we can see from our shadow here, right, r is from 0 up to 3, and so our r is going to be positive. So don't have to worry about any of that. Just simplifies down to r. Then we have our dz, and our dy dx becomes our r dr d theta. And let me slide that r. Let me write it down so we can kind of watch it happen. R dr d theta. And then this r here, let's slide it out and combine it with our other r, and we'll get r squared. All right, and here we are moving r from 0 to 3 and theta from 0 to pi. Everything's set to integrate, and we can start in. All right, so our inside integral is very quick. R squared is a constant with respect to z, and so we get r squared z, evaluated from z equals 0 to 9 minus r squared. And so plugging in for z, we get r squared times 9 minus r squared. Plugging in z equals 0, let's get 0. And so it's going to be cleanest to distribute this to get 9r squared minus r to the 2 plus 2. And so our integral here becomes the integral from r equals 0 to 3. and theta from 0 to pi, dr d theta. All right, now working our r integral, we're going to get, 9 r cubed over 3. So 9 over 3 will simplify. We'll get 3 r cubed minus r to the 5th over 5, evaluating from r equals 0 to 3. So plugging in r equals 3, we're going to get 3 times 3 cubed, that is 81, minus 3 to the 5th. It's 81 times 3. Is it 127? No, it's not at all. We'll just leave it as 3 to the 5th. Okay, and then when we plug in r equals 0, we'll get 0. And here we're integrating this from theta equals 0 to pi. And let's just bring that over here. So integrating here, we get just a constant, so integrating this, 81 minus 3 to the 5th over 5 times theta, evaluated from 0 to pi. Let's plug it in. 81 minus 3 to the 5th over 5 times pi, and then when we plug in 0, we'll get 0. And so right here on the left is the true value of our integral that we get after we translate cylindrical and work through it. Good work today, everyone. I'll see you next time.